Up next, let us welcome our second speaker, Jocelyn Lim, who is a fourth-year student in Bachelor of Chemical Engineering with honors at Xiamen University, Malaysia. Her presentation today is titled Palm Oil Mill Effluent Waste Treatment Using Metal-Based Composite. With that, I'll pass on the stage to Jocelyn.
A very good morning to our fellow audience today. So I'm Jocelyn from School of Energy and Chemical Engineering, Xiamen University, Malaysia. So today I'd like to share on our research project, which is the photocatalytic degradation of palm oil effluent using titanium oxide and Ti3C2Tx MXene composite aerogel. So this project is supervised by Dr. Andrew. And without further ado, let us go through on the table of contents today. So I'll go through on the research background and methodology. Then we'll discuss on the research and the results and research insights, and finally conclude the presentations with our future outlook and acknowledgement. So let's go through on the research background. So with the increasing populations throughout the years, we have the requirement for energy and water is increasing year by year, and for the necessities of urbanizations. However, we face some issues in energy crisis, which is like the global fossil fuels depletions and some consequences caused by the utilizations of fossil fuels for energy production, such as greenhouse gas emissions. And also, with the increasing of populations, the requirement and necessity for water has increased from year to year. However, due to the inadequate wastewater treatments and some environmental pollutions, we have also faced another issues in water scarcity. So today, we would like to target our projects. We like to target on achieving several sustainable development goals, including on SDG 6, 11, and 12, which is the clean water and sanitation, sustainable cities and communities, and also the responsible consumptions and productions. So, in order to tackle on the in order to tackle on the fossil fuel depletions, palm oil is actually emerged as one of the clean biofuels as an alternative. However, the production of crude palm oil will actually accompany with palm oil mill effluents. So it should be highlighted that when 1 million tons of crude palm oil is built, there will be accompanied by 2.5 million tons of POME. So this POME is actually having a high number of COD and BOD, which is unfavorable to the environment. So which is also shown in the slides here, where there's a massive amounts of POME productions, it's actually difficult in handling. So in the conventional palm oil mill, we're using an open pond system for this wastewater treatment. So it will undergo a series of equalizations, anaerobic digestions, clarifying and filtrations process, which is actually ineffective and it requires a long time. So therefore, we propose on having this photocatalysis process to degrade on these environmental pollutants. So photocatalysis process is actually a process of light-induced redox reactions, which will degrade on these environmental pollutants. So the exposures of photocatalysis surface to the photon energy more than or equal to the band gap energy will also result in the agitations of electrons from valence bands to the conduction bands, which is shown here. So this will consequently lead to the formations of electrons holes formations. So when the positive holes generated in the valence bands will oxidize the pollutants or water molecules which will produce on hydroxyl radicals, and the absorbed oxygens on the photocatalyst will be reduced by these excited electrons. So in the conduction band, accepted electrons possess strong reduction ability, will react with these dissolved molecular oxygens in water or absorb oxygens on the surface of the photocatalyst materials. So this will be the mechanisms of photocatalytic degradations. So there are many photocatalytic materials in the world, and soothing material has attracted a lot of attention throughout this past few decades. So some of the examples for soothing materials will be graphene, hexagon nitride, and also MXene. So MXene is actually a soothing material found in 2011, and it will be comes in the form of transition metal carbide. So MXenes have a lot of advantages, such as high redox capacities. It will be rich in hydrophilic functional groups on the nanosheet surface, and will have excellent electrical conductivity. So different from graphene, it will be able to track the photo-generated electrons easily. So why we say that MXenes is a promising photocatalysis material is that it will consist of high catalytic properties, electronic properties, and optoelectronic properties. So as shown in the graph here, through these 10 years, the research for MXene is actually increasing from time to time exponentially. So let's go through the methodology of this study. The main precursors for for this study, we are concentrating our research in having titanium dioxide as our main photocatalyst, and MXene will act as our co-catalyst in this process. So why we select titanium dioxide is actually it poses the light proximity of electrons and holes, and it consists of a wide band gap. And for titanium, for Ti3C2Tx, it will have a tunable semiconducting nature with rich surface functional groups. So by combining on these two nanomaterials, it can enhance the charge carrier separations. So why we are going to fabricate an aerogel is that aerogel have an extremely low density yet large surface area porous structures. It consists of monolithic structures, and it can avoid intricate separation process as our conventional clarifying and filtration process. So the main precursors for this study will be the main space for the MXenes, which includes titanium, aluminum carbide, titanium oxide in anatase form, and the main reagent will be hydrochloric acid and lithium fluoride. So the ionized water will be used throughout the process, experiment. So how we produce this titanium oxide Ti3C2Tx composite aerogel will first be dispersing titanium oxide anatase into the ionized water to form a dispersion. Then we'll be having an in situ HF etching for the next phase precursors to produce MXenes, and it will be dispersed in the ionized water to produce a dispersion. So when these two dispersions were mixed together, we'll have a hydrothermal synthesis to produce a titanium oxide Ti3C2Tx composite hydrogel. So after that, we'll send into freeze drying to remove the water content, and finally we'll get the aerogel. So our material characterizations will include on XRD, BD, nitrogen absorption isotope, VSAN, TEM, EDS, and GCMS. For that, we will be characterizing the photocatalytic ability of the samples by having this degradation experiment. So we'll be mixing on 34 mg of samples into a 20 ml of POME solutions and have it react in the dark environment to achieve absorption and desorption as equilibrium. After that, we'll have this photocatalytic test. So 2 milliliters of solutions will be extracted from the reactions every 4 hours for this GCMS analysis. This is for the validation of reactions mechanism in the consequent part of the study. So here is the results and discussions. So we can see that in this physics analysis, the figure here, the produced machine will have a laminar morphology of 67 nm of thickness. So this will be caused by the in situ HF etching. They remove the aluminum layer from the next phase. So we know that when we are having an extended etching and hydrothermal reaction, will cause the surface functional surface terminations by the surface groups. As shown in the equations here will be the reaction process. So when we're having this process, they will have a dispersion of nanoparticles and these surface functional groups on the nanosheet layer surfaces. So that's why we can see that nanosheet layers will have the dark surfaces. So here are the physical analysis for the MXene aerogel. We can see that the porosity has increased when we are having these nanosheet structures changing into aerogel structures. And also, the surface irregularities promotes the intimate contact between titanium dioxide and Ti3C2 MXenes. This has promoted on the heterojunction formations. So next will be the nitrogen absorptions. You can see that when we are having the titanium Ti3C2 to TiO2 Ti3C2 aerogel, you can see that the pore volume and the pore surface area is increasing. This is because of the additional porous levels that is formed during the morphology change from nanosheets to aerogel structures. It can also be observed that there's a stacking of the both porous structures, which actually enhance the porosities of this aerogel. So this is the degradation efficiency. We can obtain that when we are having TiO2 Ti3C2Tx aerogel, an efficiency of 98.3% of POME degradations can be achieved. So this is the degradation pathway we have observed during the GCMS characterizations. And it was found that the hydroxy radicals and superoxide radicals plays an important role during this photocatalytic degradation pathway. And this empirical formula will be the final photocatalytic reactions obtained from our experiment. So finally, we'll go through on the research impact and future outlook. This study can contribute to the current POME as a more time-saving and lower cost and higher efficiency POME waste treatment method. And we have provided some new insights on the fabrications of this TiO2 Ti3C2Tx composite aerogel and the application for organic pollutants. So we pioneered the applications of MXene-based photocatalysts in POME waste photo treatment, and we have also achieved we target to achieve on this SDG 6, 11, and 12. So for future studies, we will have some optimization of the photocatalytic degradation process parameters, and we'll investigate on the probing charge transfer mechanisms at the interface of titanium oxide and Ti3C2Tx MXenes, and finally investigate on the effect of TiO2 loading percentage on the photocatalytic degradation process. So I'd like to thank on this our support for this study, Dr. Andrew and Prof. IR Dr. Muhammad Aslan bin Hussein as our collaborator and some research assistant and our seniors. And this is the reference news, and thank you.